All right, good evening, everyone. So during the talk, please feel free to ask me questions, or if I speak too fast, let me know. Tonight, I'm going to tell you about the galaxy cluster called Elgordo, which you can see on the background of this slide. The study of Elgordo is part of my PhD thesis. And for those of you who don't know, Elgordo actually means the fat one in Spanish. Luckily, my collaborators decided to name this in Spanish instead of in English, or it would be a really interesting term to see on a PhD thesis. And in just a moment, I'll tell you about why me and my collaborators have been studying Elgordo and how Elgordo becomes so massive. Let me start by first explaining what exactly is a galaxy cluster. It is something very large and massive. And for us to be able to view an entire galaxy cluster, it also has to be something far, far away. So if a galaxy cluster is so massive, how was it formed? To answer this, we'll have to look at some of its smallest components. It's something that you all are familiar with. Let's talk about stars. At around 0.1 billion years after the Big Bang, there were dense regions of clouds in the universe. Well, I mean dense regions of gas, not clouds. If conditions were favorable, a gas cloud like this could collapse under its own gravity and become a star. As you can imagine, there could be many dense regions in the universe for lots of stars to form close to one another. When there's an overabundance of stars, the stars could revolve around one another, collapse under gravity, and form something called galaxy. The first of such galaxies were formed at around 500 million years after the Big Bang. An example of a galaxy would be the one that we live in, called the Milky Way. As you can see from this artist's conception of Milky Way, the sun is actually one of the many stars in the galaxy. And for those of you who have been to the dark parts of the countryside, you should have also seen the magnificent belt of Milky Way across the sky. That is actually a sideway view, not, well, we are unable to see the whole dish from within. In fact, there are around 10 to 11 stars, or around 100 billion stars in total just within our galaxy. So each galaxy is really made up of many, many stars. And if there are many galaxies around one region, such as in this view of Elgordo, the galaxies could attract one another and form a cluster. The first of such galaxy clusters were actually formed later than the first stars or galaxies, at around 3.3 billion after the Big Bang. However, the first stars and first galaxies are quite hard to detect. It's even harder to confirm their age. So what we know about the first stars and galaxies are quite speculative. Galaxy clusters, on the other hand, are bigger. They are a bit easier to detect. Therefore, we can confirm the age of the galaxy clusters with better confidence. They are some of the oldest astronomical objects that we're familiar with. Furthermore, they are also the largest structures to be able to held stably together by gravity without falling apart. Each of them typically consists of tens to hundreds of galaxies. And the member galaxies actually do not sit still. They would orbit around the cluster, just like how Earth would orbit around the sun. Unfortunately, we'll not be able to view the motions of the galaxies within a cluster. This is because it would take them 1 billion years to get from one side of the cluster to the other side. And for us to see any significant changes in their motion, in their position, it would take several million years. So even though we can take many pictures of a galaxy cluster, the view would remain roughly unchanged. An other astonishing thing about a galaxy cluster is that the numerous galaxies actually only take up 5% of its total mass. The second major component of a galaxy cluster is gas. But the gas particles also only take up 15% of the total mass of the cluster. There's a third mystery component of a galaxy cluster called dark matter. It takes up around 80% of the total mass of a galaxy cluster. And I can see a few blank looks in the audience right now. That's also my first reaction when I heard the term dark matter. I'm sorry that dark matter is such a funny name, but the name is actually quite appropriate for what it is. Dark matter actually does not emit or reflect any light. Dark matter is invisible. But that does not mean it's not important or interesting. In fact, we know so little about dark matter that any improvement in the knowledge would be a huge breakthrough. In fact, if anyone can find out the true identity of dark matter, that person would almost be guaranteed a Nobel Prize in physics. So if you want that Nobel Prize, you better pay attention to the following slides. One of the few things that we do know about dark matter is that dark matter likes to pull things towards itself. Turns out, if we point our telescopes to look at large patches of the sky, we'd find the distribution of galaxies to resemble insects that are caught on a giant invisible web. With the use of simulations, astrophysicists now understand that this invisible web actually corresponds to the underlying dark matter. This giant web of dark matter actually had a key role in structure formation and the formation of galaxies. Without dark matter, there would not be enough gravity to pull the stars to form galaxies. And the galaxies would not have formed at as early as 0.5 billion years after the Big Bang, but at a much later time. In the simulations, astrophysicists were also able to find that galaxy clusters correspond to the densest regions of this dark matter web. Since the majority components of a galaxy cluster is dark matter, galaxy clusters are really great astrophysical laboratories for us to study the properties of dark matter. And this is also the reason why my collaborators and I have been studying systems like Elgordo. We really want to understand more about the dark matter through the motions of the galaxy cluster. Now, how do we study a galaxy cluster such as Elgordo observationally? An easy answer is that we need to find out the different components. Out of the three main components of a galaxy cluster, let's talk about how to find the galaxies first. For understanding the galaxy properties, we have to collect light from them. But not just any light, not even just an image like this. We need fine spectra of light. Our requirement for the instrument is further complicated by the fact that our target galaxies, such as the one shown here, are actually very, very dim. They have an apparent magnitude of around 20, which is around 1 billion times fainter than the reference star Vega, which is one of astronomers' favorite reference stars. Therefore, to meet these requirements, my collaborators had to use a very large telescope owned by the European Southern Observatory, and it's down in the Southern Hemisphere in Chile. And here's a beautiful view of one of the 4 telescopes of the Very Large Telescope. By the way, since professional astronomers are not particularly creative, Very Large Telescope actually corresponds to the name of the telescope, and it's not just a description. Anyway, the Very Large Telescope has a very large mirror spanning a diameter of around 8.2 meters. Using this very large mirror to collect the faint light, my collaborators were able to capture fine spectra of light of these galaxies with only 40 minutes of exposure in several wavelength bands. And in order to capture these fine spectra of light, my collaborators made use of a special instrument called the spectrometer. I won't go through all the technical details of how the spectrometer works, but there is a component of the spectrometer that works like a prism. When the light from our target galaxy passes this part of the spectrometer, it would split the light into a fine spectrum so that we can record the intensity of light at each color, or what we astrophysicists call different wavelengths. And features on different parts of the spectrum actually shows how far the galaxies are away from us. For example, we can produce features on a light spectrum in the laboratory by shining light through some special chemicals. We can then compare the lab reference spectrum to a galaxy spectrum, and we would see a shift in the features towards the redder end. Now, astrophysicists have worked out that the shifts actually correspond to how far the galaxies are away from us.
So is that actually for 7 billion light years away redshift? Is that representing?
Yes, that's how we find that out.
So that this diagram is actually showing what...
oh, this is not the real data. This is just an illustration.
I'm just wondering what actually the redshift looks like for 7 billion light years away. Yeah.
It would not be very interesting to look at. It would not be much more interesting to look at than this illustration, okay. I'm afraid. Yeah. So the shift in the features can roughly be understood from this picture below. When a source galaxy emits light, it will produce features due to the chemicals on its surface. And before the light spectrum from the galaxy can reach us, it actually has to travel for a long, long time. During the journey to our telescope, the universe actually expands, causing the wavelength of the light to lengthen. This expansion of the universe would cause the light to look redder, and that's why this feature shift is also known as the redshift. By making use of this redshift as a distance indicator, we can identify galaxies that are spatially close to one another along our line of sight. So let me just circle the members galaxies of the cluster by making use of this redshift information. And here they are. I'm not sure if you can see them well. So one thing that you would immediately notice is that most of the member galaxies actually look quite small. This is because they are really far away from us. The second common thing among these galaxies is their color. Most of them look quite red instead of very blue. This is actually characteristic of the galaxies within a cluster. The rest of the stars and galaxies in this field of view are just happen to be there. They are not part of the cluster. And some of them are in the foreground of the cluster, and some of them are actually in the background. Now, let me just make a brief summary of, yes?
I just wanted to make sure I understood. So all the galaxies that are circled with red, those are all the galaxies in the cluster.
Right, they are at around 7 billion years away from us. The rest of the stuff, we can identify them as being closer to us than Elgordo, or just further away.
Ms. Ames?
Yes?
If all of those red circled objects are in the same cluster, and they all essentially orbit each other and are in the same group, is it possible to identify what would be the central area that they're all circling around, or is that difficult?
We can estimate that, and we'll see that it will be apparent where those centers would be. Yeah.
Can you point to it?
Well, I've looked at the clumps for such a long time that I kind of know there are actually 2 clumps, but spoiler alert. We'll know more about that later on. Okay.
Center of the picture will be fine.
I just want to ask, because the way when you just showed that, is it possible that like within the whole structure there are substructures that are kind of
absolutely
orbiting around themselves?
Yes,
okay.
Those are really good questions. Yeah, that could be the case, but like I said, we could only take one snapshot. It won't change throughout our lifetime, so it's hard for us to tell, like, with confidence that there are several structures like struggling with each other. Can't tell that. So let's just make a brief summary of what we can learn. So first of all, we were able to identify most of the galaxy members of the cluster. Secondly, we were able to calculate that it took around 7 billion light years for the light, it takes around 7 billion years for the light to reach us. So when we're looking at this picture of Elgordo, we're actually having a glimpse of how the universe was like when it's just half as old as now. Now, these are not the only things that we can learn from Elgordo. Remember, a galaxy cluster is also 15% gas, like I mentioned before. So let's try to look at the hot gas too, which is not directly visible here. So what's going on? As it turns out, in order to study the gas, we'll have to look at another wavelength range called the X-ray. The Earth's atmosphere is actually not transparent to X-ray, so we have to do something in space, such as NASA's X-ray Observatory. Is there a question? No? And there is a reason why we have to look in the X-ray range. From the laws of physics, we know that normal objects would radiate a continuum of light, but not just in any wavelength, but a wavelength range that corresponds to the temperature of the object. This might scare you because we don't usually see people radiating, but don't worry. Objects have to be about as hot as our sun to be able to radiate in the visible wavelength range. The lights that we usually see, they are reflections of other light source. Anyway, if we cannot see something in the visible wavelength range, we better look at the wavelength range that correspond to the temperature. This principle is also the reason why people can make use of night vision goggles. Let's say, if you're trying to find your dog in the dark, you can use a night vision goggle. And when you see through this night vision goggle, you're actually seeing the light that is emitted by your dog in the infrared range. And the so-called colors actually match the temperature of the different body parts of your dog. Similarly, the gas component of Elgordo is not at sun's temperature or in the infrared wavelength range. So we have to look in another wavelength range that correspond to the gas temperature, which is the X-ray range. So now let's use Chandra telescope as our night vision goggle to see what we can find about the gas. And we might have to wait for a while. It actually took 16 hours of exposure for the Chandra X-ray telescope to be able to recreate a thermal map of the gas. Well, just kidding. Okay, let's just see the map. And let me color code the part of the gas so that the colder part is in white and the hotter part is in red. So how hot are these regions exactly? From the detailed analysis of the X-ray thermal map by my collaborator, we found that the reddest, hottest part of the gas actually corresponds to a maximum temperature of around 100 million degrees Fahrenheit. That's around 10,000 times hotter than our sun. While the colder part of the gas, labeled as the cool core, is still incredibly hot. The cool core part is at around 10 million degrees Fahrenheit. Furthermore, the X-ray emission of the gas shows very interesting features, with two tails actually pointing to the right of the picture. To be more specific, we can compare this morphology of the gas to how a boat would create turbulent waves as it passes through quiet waters. So now, with a better view of the gas morphology, we can tell with higher confidence that the components of Elgordo are actually not at rest. There's definitely some high velocity motion going on along this axis. To verify this hypothesis of the high velocity motion, let us also look at the remaining majority part of the cluster, which is the dark matter. For this purpose, we had to make use of the famous Hubble Space Telescope. As you may know, Hubble Space Telescope is one of the most famous NASA missions. It detects light in the near infrared to the visible wavelength range. The Hubble Space Telescope was launched in the year 1990 and has had several surface missions. And after all these years, it still produces some of the highest resolution image that allows us to study a faraway system such as Elgordo. For instance, this image taken by the Hubble Space Telescope corresponds to an apparent size of around 3 arc minute by 6 arc minute. If you hold out your arm, the nail on your little finger would correspond to a size of around 1 square degree. And the apparent size of this image is around 200 times smaller than that nail. And yet, the Hubble Space Telescope could resolve objects from such a small patch of the sky so well. This image quality is unmatched by any ground-based telescope. This is because light from galaxies does not have to pass through the turbulent atmosphere before they get to the Hubble Space Telescope camera. Anyway, so I was saying that we could use this picture to find dark matter. But isn't dark matter dark? Then how do we see it in the visible wavelength range? Turns out, Albert Einstein, the famous physicist, has predicted that in 1912, that massive objects, such as a dark matter clump, would distort the space-time around it. As a consequence of the distorted space-time, the paths of light that travels around dark matter would also be bent. In other words, the invisible dark matter would act as a lens to the background light source. Now, imagine this candle as your distant galaxy. If there's dark matter in the foreground between us and the candle, the dark matter would act like this wine glass. The image of the light would be distorted according, and the dark matter, and as we can see, the image would be distorted according to the orientation of the wine glass, such as how the light source from the galaxies would be distorted according to the distribution of dark matter. If the distribution of dark matter is very symmetrical and the focus is suitable, we may be able to see the resulting image as a giant ring. And since Einstein was the first person to propose the distortion of space-time, this ring is also known as the Einstein ring. However, most of the time, the distortions would not be so perfect. As you can see, some of these distortions would result in multiply lensed images. And sometimes the images would also be displaced from the original position of the object. And just to get the terminology out of the way, this bending of light by dark matter is more commonly referred to as gravitational lensing. And if we look more closely at the Hubble Space Telescope image of Elgordo, we can tell images of background galaxies being distorted like the candlelight. For example, this arc of light actually corresponds to a stretched image of a galaxy. With more careful studying, astrophysicist Dr. Sachin and his team were actually able to find 27 of such displaced images in this picture. That would correspond to the gravitationally lensed galaxies.
So for that type of image, is it possible to take a spectrum of that gravitationally lensed image?
Yes, it should be possible if you have a really big telescope that you can
So they were able
ask time for.
to determine that these were in fact be further away.
Yes.
Okay.
They have to be further away in order to be stretched like
Yeah.
this. If they're like closer to us, then they
Right.
would not be lensed at all. Yeah.
Can I ask a question? Is it then that dark matter is evidenced by this kind of lensing? Is it because we see lensing that we think there's dark matter?
Yes, that's part of the evidence.
That there's something out there
Yeah. Well,
that we can't explain?
Yeah,
and-
there are several other experiments that confirm the existence of dark matter. This is not the only one, but we won't have time to go
Okay,
through those.
cool.
Yeah.
Dark matter, is it transparent to all frequencies?
Light, yes.
Light?
Yeah, it does not emit in any wavelength,
And then also it's blocked.
and it does not reflect light. Light just goes through it. Yeah.
Sounds like my last boyfriend.
One question.
So
Yes.
it's not gravity that's bending the space-time, it's dark matter actually.
Well, the dark matter exerts the gravity that bends the space-time. Yeah, you're making good connections.
Okay.
Now, the majority of galaxies in the background of Elgordo are actually not as highly distorted as the ones that I've shown. Many of the galaxies that are lensed by Elgordo still look like normal galaxies. The distortions to their images are harder to detect, but the distortions are still there. The distortions would actually stretch them lightly according to the dark matter distribution, and so that they would align more tangentially along the edge of the dark matter halo. And just this past spring, my collaborator James G. and I actually conducted a study to investigate these smaller, less noticeable distortions. By making use of computational and statistical techniques, we're able to detect and quantify all these tiny distortions and make this map that you can see over here in blue. And I've colored it so that the denser regions are actually shown in lighter blue, and the less dense regions are in darker blue on the outer edge. By summing up all the mass distribution in this map, we're able to determine the total mass of Elgordo as 3 times 10 to the 15 solar mass, or what we know as 3 quadrillion solar mass. This is an astonishing number because Elgordo was found in such an early age of the universe. As I mentioned at the beginning of the presentation, structures were formed by a merger of smaller objects. It is very rare for objects to have clumped so quickly to form such a massive galaxy cluster. And indeed, Elgordo does not seem to be a static object. We can identify Elgordo as a merging cluster with 2 mass clumps. And as if all the evidence is not concrete enough, a team of astronomers led by Dr. Menento actually found signs of shock waves, which I've overlaid in yellow here. This further confirms the view that Elgordo is a merging system, because there's just no other astronomical objects that can emit radio emissions like this. The radio emission highlighted here alone spans 1.5 million light years. That's at least 10 times as long as the diameter of a regular galaxy. The radio emission patterns just does not match any high energy events in the universe, except for a merger. Combining all the information from different wavelengths, we're able to infer that Elgordo is very likely to be feasting on a neighboring galaxy in order to get so fat. With the help of simulations, we think we now have an idea of how the feasting occurred. And here's a brief cartoon to show you how we think the merger occurred. In this cartoon, I've represented the galaxies with a yellow oval shapes, and the purple clump would represent the gas and the dark matter. We postulate that the progenitors of Elgordo could be two nearby galaxy clusters. The two clusters were so close that they got attracted and accelerated towards each other due to their mutual gravity. As the clusters approached each other, the huge acceleration due to gravity builds up huge pressure within the cluster, creating some shock wave that propagates along the merger axis.
What's the medium it's propagating in?
It's actually the gas. When the cluster finally passed each other, we estimated that the system would have accelerated by gravity to move at around thousands of miles per second. At the same time, the merger shock wave would start propagating outwards. Amazingly, during the collision, different components of the cluster actually interacted differently. Since there were so few member galaxies, they are actually spaced very far apart from one another. Therefore, during the collision, they actually did not collide. They just went right through one another without slowing down. On the other hand, the gas particles interacted much differently. The gas particles could bump into each other and get very, very hot. Like I tell you, it was like 100 million degrees Fahrenheit. Furthermore, since the gas particles could bump into each other, they were slowed down and started to lag behind the galaxies. A very interesting thing that we noticed from this is that the dark matter actually moved more like the galaxies and not the gas particles. This suggests that the dark matter actually has very little interaction with the gas or other dark matter particles. The dark matter can move through galaxies and other dark matter particles just like a ghost without interacting at all. But is that really the true story? We don't know. This area of research is really the forefront of dark matter research nowadays. My collaborators and I are still trying to quantify how strongly dark matter would interact itself through the study of colliding clusters such as Elgordo. Hopefully, by putting quantitative constraints, this types of study would be able to help physicists to narrow down the number of dark matter candidates and eventually find out the identity of dark matter.
Question?
Yes?
Backing up a little bit.
Okay.
So this intergalactic gas is about 60 million Kelvin? Or 100 million Fahrenheit. I'm trying to think of that in Kelvin. But anyway, how does that compare to normal intergalactic gas in other superclusters? Is it hotter?
It depends on which galaxy cluster that you're talking about. And even if we look at merging systems, I think the Elgordo is a bit hotter. It's like around 10 times hotter or so. Yeah. Yes?
If there's a certain amount of kinetic energy in those clusters before they hit in the galaxies and the stars and the gas and whatnot, and after they hit, how much of that kinetic energy is turned to heat? Like, is it 10% of the kinetic energy, or 50%? Well, or 1%? I just want a feeling for how.
that would be a wonderful question to answer, but since we do not know how fast they were moving originally, we can't really do that calculation.
Not for another symbol.
Yeah, I'm sorry. Yeah.
Well, I mean, they can calculate the energy in the gas, that hot gas cloud where it says red, they can calculate the energy in the red gas knowing its temperature and its volume and whatnot, and they can kind of estimate the kinetic energy of the cluster just by
Yes,
counting
actually
the
that's
number
how we do our simulations, by
Yeah.
estimating the energy loss or how the energy convert from one form to another.
Yeah.
But yeah, I don't have a feeling for that.
Okay, good.
Not for the gas.
Thank you. It's okay.
So the entire simulation is based on the shock waves that you've detected by radio.
No, actually, I have left out a part of the picture here. Well, and this is also related to what you've talked about the kinetic energy. So when I talked about the redshift of the galaxies, we can actually infer how fast they're moving relative to us. So we can estimate their velocity. And that's part of how we calculate the kinetic energies of these clusters. And by assuming their 3D configuration, we can actually convert that kinetic energy at that. So let's say. So between here to here, we know how far that distance is. And we know around how fast the galaxies were moving.
Mm-hmm.
So we can actually calculate the kinetic energy. And by knowing how far the galaxy clusters were at this observation, we could calculate something called the gravitational potential energy. And by energy conservation, as long as we know those two terms at a particular time, we can actually extrapolate forward in time or backward in time in order to calculate how fast they would be colliding. And that's how I got the estimates of the cluster moving at thousands of miles per second.
I'm sorry, I was just curious, if there's several layers of dark matter between Elgordo and our telescope, would that skew any of those results at all? Or do we know
Definitely, definitely. So when we were looking at the redshift distribution, I don't have a plot here with me, but we can actually plot the redshift distribution of all the galaxies along a line of sight in this field of view. And if we make that plot, then we would see that if it's very close to us, there's like some galaxies with redshifts lower than the redshift of Elgordo, and there would be a peak at the redshift of Elgordo, showing that there's only significant structures around where Elgordo is. That is a totally valid question, but we have looked at that. Okay, so in summary, by making use of multi-wavelength observations and simulations, we're able to confirm Elgordo as one of the oldest, most massive merging galaxy clusters. The dark matter components of Elgordo acted like a big lens to magnify background galaxies and has allowed us to determine the mass of Elgordo. And most importantly, the special merging nature of Elgordo has allowed us to understand how dark matter behaves under extreme conditions. Even though Elgordo is not the only merging systems that we study, its high mass and simple configurations makes it one of the most valuable samples out of all the samples that we studied. And this concludes the part of my talk about Elgordo. Since we still have some time, let us also look at some pretty pictures of other merging galaxy clusters. I have to show them off because they're so pretty. Yeah, I mean, like during technical talks in the university, I would never show them because like people would just not be interested. But,
We love it. We love it.
okay,
yeah.
so here we go. This is the first one, and this is actually the most famous galaxy cluster. This is the poster child of detecting dark matter because there's like a clear separation between the gas and the dark matter distribution. And are there any guesses of what this cluster's name might be?
Coma cluster?
Virgo?
Bullet cluster? Yes. So if you look at this shape over here, it kind of looks like a bullet. So people just named it as
Where is it located?
the bullet cluster. It is somewhere in the northern hemisphere. Sorry.
I have a question for you on the Elgordo cluster. The elements that make up the galaxies in that cluster, are they considered primeval and lacking in heavy elements, or is this, by the time 3 billion years passed, have the star systems in this cluster been manufacturing all the heavy elements? Are they in the same proportions as we find in the more modern universe closer to us?
I think it would be similar. So, as I mentioned, the galaxies in Elgordo are actually quite red. Let me try to show you that particular slide. So it depends on how you defined modern universe. Okay, so here they are, they're red. The red color actually means that they have suppressed star formation. Because if they're actively forming stars, they would look bluer. So it depends on which part of the modern universe you're looking at. Yeah, so that they have already manufactured a lot of stars. They are not the first generation of stars. They should be normal stars that we can see.
So then they've gone through enough
like cycles.
Yes,
to
have as much of a distribution of all the elements
yes.
as Milky Way.
Yes.
Okay.
It would be maybe a bit further along, I would say. Because if you look at pictures of Milky Way, it's still kind of blue and forming a lot of stars.
Sure.
But here they are like, they look quite red.
Well, that would just be a factor of the age of it as well, right?
It could be.
Stars have gone through their cycles. Most of them have gone over to the red.
Yeah.
Or they've blown up.
Just I want to confirm something I think you said. To ascertain the velocities of the two clusters with respect to galaxy clusters with respect to each other, would you say you determine that by looking at the temperature of the shock waves through the gas?
No, actually, it's very hard to determine the velocities through the shock wave.
But you said you managed.
We have to look at the. So when I talked about the redshift, I was actually hiding something. I was not telling the whole truth. So there are two parts to that. Why there is a feature shift. The first part is due to why the universe expanded when the light is propagating towards us. The second part, why there is a redshift, is because there might be some motion of the galaxy relative to the cluster. They could be moving.
I didn't mean radial. I meant with respect to each other.
Right, so we have to, the only way that we can estimate any velocity of the galaxy is along the line of sight. Remember, like, even if we take pictures of the galaxies, they would not move very much at all. So we cannot detect velocity of the galaxies along the plane of the sky. We can only detect them radially. And we'll have to guess what's the inclination in order to guess the 3D velocities.
You could determine the velocity, say, perpendicular to the radial direction with respect to each other.
Right.
We were talking about kinetic energy.
Right.
You have to know the
Right, so
velocity.
we have to assume a particular angle of the inclination of the merger axis of Elgordo relative to us. And we could,
Oh, I see.
okay. So. Okay, so if we circle all the galaxies from this mass clump and estimate the radial velocity, and we circle all the member galaxies in this mass clump and estimate another radial velocity, those two radial velocities would actually be slightly different. And by assuming a particular angle, then we can use the trigonometry tricks in order to calculate what is the free d velocities, so that we can recover that information. Yeah, that's a good question. Thanks.
The bullet is in the constellation Carina, which is the southern hemisphere.
Oh, okay.
Oh, thank you.
Gordo is in Phoenix.
Yes.
Further south.
Where is it?
Phoenix.
Phoenix, yeah. It's harder to
Arizona.
Yeah, it's harder to obtain any data for Elgordo just because it's in the southern hemisphere.
I was interested in the color, the coloring of this particular photo. Does that represent a temperature change or just a frequency range, like from infrared to radio waves?
Okay, so the red actually represents the X-ray emission of the gas. The blue actually represents the dark matter, just like we described earlier. The density change is complicated. The color change is actually complicated. It depends on the density of the gas, and it actually also depends slightly on the temperature. So it's a combination of both, and we can't quite disentangle those two effects. But for the blue clump, it does correspond to the density of dark matter only. Well, okay. Let's move on to the second one. Okay. So this cluster is actually discovered after the bullet cluster. And it also has the characteristic look of having two dark matter clumps on the sides with the gas distribution sandwiched in between. So are there any guesses in the audience of what the name of this cluster might be? Sandwich? Oh, that should have been the name. Too bad. Astronomers, professional astronomers. Baby bullet, yeah. I'm not quite sure that I see a baby bullet anywhere. I think it might be named because the term bullet seemed popular at that time, and it might be able to raise some interest in the funding agencies. Yeah. All right. Here's the third cluster.
Magic bullet.
Good guess. Okay.
Silver bullet.
Armor piercing.
This cluster was actually discovered by one of my groupmates at UC Davis. The dark matter clumps look less circular, but you can still tell that there are two dark matter clumps with the gas sandwiched in between. He chose to name it as the musket ball cluster. Yeah, he said that it looks more like two musket balls being thrown at each other instead of bullets. So.
Okay.
So that's a collision also.
Yes, all these three have been.
These are all collisions.
They're all post-collision.
Yeah, they're all post collisions.
Is gravitational lensing showing up in these?
Yes, gravitational lensing is how we come up with these map of blue areas.
Okay. But no distorted lines or anything like that?
We don't see highly distorted lines in the musket ball cluster. I think we do see something heavily distorted in the bullet cluster. Not trying to find where they are. I think for the beta bullets, this might be quite strongly lensed. No giant arcs though. And this last one, I'm just putting it here to show you that merging clusters does not have to be in that nice, simple shape with two dark matter clumps on the side with the gas sandwiched in between. Sometimes the merger can be a lot messier. And there's just no clear separation between the gas and the dark matter clump in this one. And the name of this cluster is actually quite appropriate for what this is. It is the Pandora's cluster. Yeah, so if anybody knows about the Pandora's story, the guy who discovered this cluster said that it looks like the evilness that has leaked out of the Pandora's box.
Ms. Ng, does the Pandora cluster emit radio waves?
Does it emit?
It's a stupid pun, I'm sorry.
No. It might. No. It might, but we don't see that giant shock wave on the side as Elgordo. It's actually quite. It's quite characteristic for Elgordo to show the two giant arcs on the two sides. Elgordos is one of the first cluster to have those two giant shock waves on the side. There are more clusters that are coming up that we are going to analyze. But we don't have the pretty pictures for them yet. We haven't done all the analysis to map them to blue colors or red colors. But you can look them up on our website. My collaborators and I actually maintain a website at UC Davis. And here's a URL. You can go on the internet and type this in your cell phone. And you can find more about our merging samples. One of them is called the sausage. The other one is called the toothbrush. And those systems all have the characteristic radio emission, the shock wave features on the outer skirts. And those are really exciting because we think that with the shock wave, we can really constrain the configuration of the mergers much better, because in order to see the shock wave, the merger axis really has to be in the plane of the sky instead of like pointing at us. The merger cannot happen in this direction for the shock wave to be so visible to us. And for those of you who have a cell phone, you can actually scan this code and it will take you directly to the website.
I have a question about the one frame that circled all the galaxies in the Gordo cluster. It looked like there were several dozen. Is there?
There are 89.
Does that represent most of them, or there are others there that just weren't identified yet?
That's a good question. So in order to obtain the redshift information, we actually have to put the observation is actually set up quite in a quite confined way. We actually have to block the light from most other stars and galaxies in field of view. So we have to target them. So these are selected regions that we collected light from, and there are many others that could be potentially in the cluster that we did not collect light from. Yeah. And if we have infinite telescope time, would definitely go after these other potential members, but we don't, unfortunately. Yes?
You know, those of us who are baby boomers would appreciate if you could name these clusters after early rock and roll stars. Jimi Hendrix or something like that. That would assure your funding.
Okay. I'll try to tell the people who are trying to learn these, but I don't know. Yes?
Are there new instruments that are going to be coming online in the near future that are going to help you explore these merging clusters in new ways? James Webb or ALMA or anything?
James Webb would look in the near infrared range. It might help us narrow down the redshift information a little better. And the ALMA is actually an array of radio telescope. That would also help us to see the radio emission that is due to the shock waves. So the answer is yes. And these upcoming telescopes are actually, most of these big telescopes are actually scanning the sky. Some of them are scanning the sky. So they would not only help us study individual ones, they would help us discover the systems by, like, when they just scan, they see something abnormal, and they would be able to tell other astronomers, oh, there's something abnormal, we should look at that patch of the sky. Yeah, so yes, definitely.
On your last, or in the summary, the last thing was we have a better understanding of dark matter. Is that it's fairly unaffected by other dark matter, galaxies and gases, or what exactly have you learned about dark matter?
Exactly. Okay. So the quantitative constraints actually come from seeing some separation between the different components. So it wouldn't be very impressive for us to tell you how the so-called interaction number, but we could actually calculate something called a cross-section, interaction cross-section among the three components. We know gas, for the gas, it's a pretty high number. And the galaxy is a pretty low number, like 0.1 or 0.2. And right now, we can put this number at around 1 in some units. And we're trying to lower this particular number. And by knowing this number, the physicists who are still using pen and pencils and calculators to calculate what particles could make up these dark matter, they could really rule out some of the candidates by comparing this interaction number that is predicted by their theory. So in that sense, we're helping the dark matter search.
So I really appreciate the scale you gave us, 0.3 and 1, and then the gas is 200 or 20?
It is a huge number.
Oh,
yes.
2,000 or something like that then.
Yes,
Okay.
it's a huge number. Yes?
So for galaxy clusters, is there a typical number of galaxies in a cluster, or is there a large amount of variability in the number of galaxies in a cluster?
There are some range. It's like either, if it's below 50, it's called a group. If it's above 50, or in the range of 100 and 200, it's called a galaxy cluster. And there are actually different classes of galaxy clusters that you can look up, and they're called the Abel class. And yeah, if you want to look them up, you can. Yes?
Is there a way to detect galaxy clusters before they merge together, like pre-impact? And also, when was the Gordo cluster discovered?
The Virgo cluster. Okay, yeah, so we do see some pre-mergers, and the way that we tell that there are pre-mergers is that the gas is not as hot, but there are like several clumps close to each other. And we can tell maybe there are pre-mergers. And can you repeat your question about the Virgo cluster?
How was the Elgordo cluster discovered?
Oh,
or when and how? Yeah.
It was in the year 2007, and you caught me. To explain that is another very long story to explain how it got discovered.
Maybe people can come ask you after the meeting.
Yeah, that could work too.
I think you explained it earlier. I think you said it basically there was an anomaly that was noticed, and so then
yes, the anomaly is detected in the cosmic microwave background.
Right.
And I hate to bring another term that is not
really
known by most people.
Yeah.
Yeah, but we do see some anomaly in some signals when there are like large telescopes scanning across the sky,
Right.
and that's how we first discovered it. And then later, astronomers decided to follow up the anomaly by pointing X-ray telescopes at that particular patch of the sky.
Right.
And then we further confirmed that there's definitely a galaxy cluster. Yes?
About colors. Sorry about the ignorance, but I used to know that, like, for stars, the colder the color, the hotter it was. So now it's reverse for gas. So is it because it's X-ray, or just because I didn't understand it?
The color, okay.
Like for gas, here, everything that's hot is red.
Okay, so this color is a thick color.
Yeah.
I have coded it in. It's not really the real color. It's in the X-ray range. We can't actually see these colors. So it's just due to the way how I presented the colors. It might be confusing. But if you want to see, well, this is also not a very good image, but the cooler something is, the redder it is. The hotter something is, it's bluer.
Yeah, that's
it's
what
quite,
that's why I was confused.
yeah, contradictory to common sense, but that's how it goes.
Yeah.
Yes?
What's next? What do you want to know about?
What's next? There's several things. First of all, I need to make better maps, quantitative maps, to actually quantify the separation between the galaxies and the gas and the dark matter in Elgordo, and really calculate a number for the theorists to compare with their theory. Second of all, Elgordo is not the end. It's just part of the bigger picture that we have. We have a lot more data from all these different clusters. So Elgordo would be part of it, and it would inform how typical Elgordo is. And since all these clusters has different configuration, we can compare and contrast to narrow down our uncertainty. So that's the next step. Yes?
So these galaxies are 7 billion light years away, 20th magnitude, and
around 20th. It might be fainter.
And thereabouts. But so in any event, it's you would not be able to detect a black hole at that faint of a level. So I'm wondering whether this extra mass that's being detected that you're thinking is dark matter could be some black holes that are
that's a good question.
in the area.
Okay, so there are actually several dark matter candidates that we physicists postulate could be part of dark matter, and they all have very cute names. MAPCHO actually stands for massive astrophysical compact halo objects. These are neutron stars, black holes, brown dwarfs, anything that could be dim enough so that they are under our detection limit, so they can't be detected that far away. So those could be part of the matter that contributes to the gravity.
Okay.
The second class are just a new type of particles called weakly interacting massive particles, WIMP. And physicists are really studying those.
Mm-hmm. Yeah, thank you.
Is the Higgs a stable particle? Will it last long enough to do something in the spot?
That I don't really know, but I know physicists are actually trying to manufacture lots and lots of them to study their properties more carefully.
Karen's going to be driving all the way back to David's tonight. We want to thank